Welcome back, everyone. Today, we're diving straight into the invisible infrastructure that literally keeps our entire digital world running smoothly. Think about it. Every time you stream a show, jump on a video call, or download some massive file, you are relying on this highly complex, completely hidden system. Today, we're unpacking exactly how it works. Network congestion control.
So think about this for a second. Why doesn't the internet just completely crash during digital rush hour? Right? Every single evening, millions of people log on at the exact same time to stream movies, play online games, and sync their devices. Now, if our physical highways handled that kind of sudden massive influx of traffic, we'd be looking at total gridlock. Cars parked for miles. No way anyone's moving. Yet, somehow, the digital highway just keeps flowing. How does the network manage the ultimate traffic jam without completely breaking down?
Well, the answer lies entirely in this one foundational concept: congestion control. Put simply, this is the regulation of data flow within a network to prevent congestion, degraded performance, and packet loss, ensuring efficient bandwidth sharing. Basically, it's the ultimate automated traffic management system for our data. It makes sure that every single device and connection gets a fair slice of the bandwidth pie, which keeps the whole network operating at absolute peak efficiency.
Okay, let's dive into this. We're going to cover 5 main things today. First, the network traffic jam. Second, goals of congestion control. Third, mechanisms for managing traffic. Fourth, dynamic control with TCP. And finally, number 5, the big picture.
All right, starting with Section 1, the network traffic jam, when too much data hits the road. Before we can really appreciate the solution here, we have to understand the catastrophe of uncontrolled data. Just imagine every single application on your computer throwing data onto the network as fast as it possibly could, completely ignoring everyone else. On a congested network, you have way more data being sent into a network segment than it can physically handle. And just like a real-world road, when capacity is breached, everything grinds to a halt. But in the digital world, this leads to what we call packet loss. Pieces of your data are literally dropped and lost, leading to absolutely terrible, degraded performance. In stark contrast, on a managed network, the rate of transmission is actively regulated. The flow is tightly controlled, and that results in smooth, efficient operation.
Moving on to Section 2, goals of congestion control, the blueprint for a well-managed highway.
Now that we know exactly what goes wrong, let's look at the blueprint of a healthy network and what it's trying to achieve every single millisecond. First and foremost, the goal is to prevent network congestion altogether by proactively regulating those data rates. Second, it has to maintain quality of service, or QoS. Third, and this is a big one, it works to avoid packet loss. Because think about it, when packets are lost, they just have to be retransmitted, which means even more traffic. Fourth, it ensures the fair allocation of resources among all users, so one bandwidth-hungry download doesn't just kick everyone else offline. And lastly, it improves overall efficiency, making sure data reaches its destination with minimal delays.
Which brings us to Section 3, mechanisms for managing traffic, the network's physical toolkit.
So we understand the goals, but how do networks actually pull this off? Well, they use a specific set of tools and digital traffic lights to keep everything moving. Now, what's really interesting about this slide is the difference between 2 primary tools, traffic policing versus traffic shaping. Think of traffic policing kind of like a strict speed camera on the highway. It literally limits the rate of incoming traffic to a specific threshold. If you cross that line, your excess traffic is instantly dropped or marked. Boom, penalty. Traffic shaping, on the other hand, is a bit more elegant. It's much more like those metering lights you see on a highway on-ramp. It regulates the flow of traffic to smooth out sudden bursty traffic patterns, basically preventing massive spikes in data transmission before they cause a pileup.
But hey, the toolkit doesn't stop there. Routers and switches actually act like active traffic cops. They use queue management, dynamically deciding whether to drop or prioritize packets that are waiting in line. Then there's quality of service. This prioritizes critical applications for bandwidth. So for example, your live video call gets priority over some background email sync. And then there's congestion feedback, where transport layer protocols are actively listening to the network. If they sense packet loss or delays, they just automatically adapt their transmission rates.
And this brings us to a really fascinating evolution in feedback mechanisms, explicit congestion notification, or ECN. Historically, the only way a router could tell a sender, hey, slow down, I'm overwhelmed, was by just dropping their packets, which, let's be honest, is a pretty destructive way to communicate. ECN acts as the network's early warning system. It's a mechanism where routers can signal congestion directly to endpoints without dropping a single packet. It's absolutely brilliant because it allows for incredibly efficient control without that destructive collateral damage.
All right, Section 4, Dynamic Control with TCP, the smart car of the Internet.
So we've talked about the overarching highway infrastructure. Now let's look at the vehicles themselves, specifically how an individual protocol like TCP reacts dynamically to road conditions. TCP, or Transmission Control Protocol, uses this thing called window adaptation. Essentially, a smaller window size indicates congestion, while a larger window size indicates more available bandwidth. Think of the window size as the amount of data the protocol is allowed to send before it has to wait for an acknowledgement. TCP is constantly adjusting this window. It's exactly like a driver easing off the gas pedal when they see brake lights ahead and then pressing down on the accelerator when the road opens back up.
Let's move to and see how this builds into an automated, chronological cycle. Step 1 is slow start and congestion avoidance. TCP doesn't just flood the network right away. It starts cautiously and gradually increases its transmission rate when it senses low congestion. Step 2, if things get bumpy, is fast retransmit. This is where TCP detects congestion by receiving duplicate acknowledgments, basically realizing a packet got lost in all the chaos. And finally, Step 3 is fast recovery, where it quickly recovers from that packet loss to maintain as much speed as safely possible without causing a larger crash. It's just a constant, highly intelligent loop of sensing and reacting.
And that brings us to Section 5, the big picture, why this invisible system matters.
We've looked at the traffic jams, the goals, the physical tools of the routers, and the smart protocols baked into the data itself. Let's zoom out for a second and look at the overall impact this has on our daily digital lives. Remember, congestion control is absolutely vital because our network resources are shared. You, your neighbors, massive corporations, we are all using the exact same fundamental infrastructure. Without this system, we would face total network saturation. By actively managing the flow, this invisible infrastructure minimizes transmission delays and ensures reliable, timely data delivery. Really, it is the only reason the modern internet is actually usable for us today.
Which leaves us with this final thought to ponder. Think about the incredible scale of what we've just uncovered. How many invisible congestion control decisions, how many queue management prioritizations, and how many dynamic TCP window adjustments were just made in the last 10 minutes simply to stream this very explainer to your screen seamlessly. The numbers are staggering. The digital highway is alive, and it's constantly adapting to keep you connected. Thanks for learning with me today, and I'll catch you in the next explainer.